Hi everyone, and welcome to our video on applications of Extrema, where we have rectangles involved. So our guidelines are these 5 steps. It's kind of similar to any word problem in math, where we just want to make sure you read it carefully and focus on what's most important here. So let's not actually read all 5 of them. I mean, you could read it on your own. Let's jump into these problems. So in this example, it says a farmer has 12,000 feet of fencing. He wants to build a rectangular enclosure next to a river where the side next to the river needs no fencing. What is the largest possible area? All right, often I like to focus on the question first, like that, so the end of this whole paragraph thing. What is the largest possible area? So largest possible area is meaning that we need to maximize the area. So I'm going to put that over here. We need to maximize area. Okay, so and in these problems, the application of Extrema, so these word problems, is as soon as you see something about maximum or minimum or something that references those, maximum or minimum, is what Extrema are. And so we know we have a process for it where we'll find the derivative and set it equal to 0 eventually. All right, so I want to maximize area, and then based on this description, it says the farmer has 12,000 feet of fencing. He wants to build a rectangular enclosure next to a river. Okay, so let's get that portion. So the rectangular enclosure next to a river. Okay, so let's say this is the river, the squiggly line, and then I want to build my rectangle right there. Okay, so it's like that. And then if you have a rectangle, well, you can label these. This is like this would be X, or it doesn't matter what letters you use. I'm going to call it X though, and let's call this Y. And then let's go ahead and label that one X as well. And so based on this picture, I know the area of a rectangle, maximize area, the area of a rectangle, let's use A for area, based on the letters that I used would be X times Y. Okay, so that's what I want to maximize. However, before we maximize it, we want it to be in terms of a single variable. Okay, so let's use this other information where it says a farmer has 12,000 feet of fencing. Okay, so if the farmer has 12,000 feet of fencing, that means we have this side X, and the side Y would add up to be 12,000. Typically, this is probably considered a perimeter, but it's not the side of the river we don't need, but I'm still going to call it P for perimeter, would be the X plus X, which is 2X, plus Y, and then they told us that the perimeter is 12,000, so we're going to change this P right here into the 12,000. So we'll have 12,000 equals 2X plus Y. Okay, and the reason that we want to do this is, well, now with this equation, I can solve for either X or Y. So we're going to solve for one of the letters here and plug it into this one. All right, so I think it's easier to solve for Y. So let's go ahead and solve for Y here. Solve for Y, which means we just have to subtract the 2X over. So we'll minus 2X to both sides, and we would get, let's just put it over here to make sure I've got enough room. Y would be equal to 12,000 minus 2X. Okay, I'm going to cloud it. Okay, and so once we solve for that, now that I have this, now I can go back to the focus of the problem, which was to maximize the area, but I can now change that Y to make it into an equation with a single letter. So the Y, we're saying, is 12,000 minus 2X. And then now I can start to simplify this area formula. So our area is equal to, the X would distribute, so I'd have 12,000 X minus 2X squared. Okay, so this is our area formula now that it's in just a single variable. And now that it's in as a single variable, now it's easy to take the derivative of. So going back to what Extrema means in calculus, it usually means find your derivative and set it equal to 0. So let's find the derivative of this. So this one's pretty easy. I'm going to use A prime equals, the derivative would be 12,000 minus 4X. And then once you have your derivative, well, set it equal to 0. So 0 equals 12,000 minus 4x. And then now we could solve this. I could add the 4x over. So I kind of ran out of room. Let's put it up here. I could add the 4x over, though, and we would have 4x equals 12,000. And then if we divide by 4, we would have x equals 3,000. Okay, so that's our x value. So let's go back and so this would be in feet. Let's at least put our units on it. And I'm going to cloud it. It might be an answer, it might not be. Let's make sure we answer what they want. All right, so let's read it again. So a farmer has 12,000 feet of fencing. He wants to build a rectangular enclosure next to a river where the side next to the river needs no fencing. What is the largest possible area? Okay, so the largest x, or the x value that I found is 3,000. So I didn't answer the correct thing that they wanted yet. So they said, what's the one of the sides? Well, we have that. Well, one of the things we could do is use our perimeter to plug in and get y, or we could just go back to the start equation right here. Okay, so it was nice that I started. Now I'm making some type of symbol around it, where I have the area, and so if I want to know the largest possible area, I'll plug the 3,000 in to my area equation here. Okay, so now let's plug that in. Okay, so our max area is equal to 12,000. So I'm using that equation times the 3,000 that we just found for the x. So now all I'm doing is just changing those x's. Minus 2 times 3,000 squared. Okay, so that is our max area, and then this is just going to be plugged into a calculator. So our max area is, let's just go ahead, I'm going to use the one that's just on the computer here. Okay, so 12,000 times 3,000 minus 2 times 3,000 times another 3,000. So 3,000 squared, I'm just doing it like that. And we get 18 million square feet. Okay, so it's a lot of feet. That's okay. Or there was a lot of fencing, it seemed like. So 18,000 square feet is our final answer here for that area. So we have 18 million feet squared. Okay, so that's that. So we found what they wanted. There we go. Okay, and if they needed to, say they wanted the dimensions, well, you could go back and plug 3,000 in to your perimeter equation to get your y. Okay, so if they did want that, just to show it, the y would be 6,000 feet. So if they did ask for that, it would have been 6,000. Our x is 3,000. So in case they asked what are the dimensions of the largest possible fencing that provides the largest area, well, then you would say 6,000 feet by 3,000 feet. Okay, so just be careful of the way that it gets answered. Okay, so there's an example. This is a very famous, they love this type of problem where we have three sides of a rectangle. One side is occupied by something else. It's usually broken down in this way, no matter how they word it. Okay, so let's see one other style problem with a rectangle. So in this one, it says a rectangular piece of cardboard has dimensions 30 by 20 inches. Equal squares will be cut from each corner so that the board can be folded into an open-top box. What should be the length of a side of each square to maximize volume? Okay, so I see this, maximize volume. Okay, so, and they use the word maximize. Okay, so maximize volume. Okay, so, and if what we've got, we're maximizing the volume of a box, they said an open-top box. Okay, so that means I have, let's try to draw a box here, 3 dimensions, the best I can. How's this looking with my computer pin? Not too bad. Okay, so that's a box. Okay, so, and it's open, so let me at least show, there we go. Okay, so the top is open. All right, so I have a very poorly drawn box. It's okay, I guess. Okay, so, but let's go back. So that's our box, and I don't want to label any dimensions yet because it looks like it's from the rectangular piece. Okay, so let's take this. So they're taking the rectangular piece of cardboard, has dimensions that. And so let's put this over here. So I've got a rectangle. with 30 by 20 inches. And then they're saying equal squares will be cut from each corner so that the board can be folded into an open top box. Okay, so they're taking a square out of each corner like this. And then they're saying what should be the length of a side of each square. So these are my squares in red there to maximize volume. Okay, so the what should be the length? So we don't know what that length is. That's x, or I'm going to use x. And since it's a square, I know that these are all length x. Okay, so all of these are length x right here, really all the way around. Okay, so just to make it, I'm going to mark there. Okay, so I didn't mark every single one. I marked all of that square, but all of them are all x by x by x by x. Okay, so they're all x's. Okay, anyway, so it's going to get folded up. All right, so these are going to get cut out, and then they're going to get thrown out, I guess. And then afterwards, we're going to fold up. Okay, so it looks like if these are getting, so it's tough with the two-dimension picture here, but it looks like this part and this part would be part of the base. Okay, so this part is part of the base, and notice that, well, the whole thing in the, so I bolded this in the black. This is not 30, that's bolded in black. From there all the way to there is 30. And so what I need to do is figure out what this bolded black portion is in our picture. Well, it looks like if I took away an x and I took away another x, I would have that this bolded part, so let's put it up here, this bolded part is 30 minus 2x. Okay, because again, I took away that x, and let's go ahead and just put an x there, and that x were taken away from the 30. So 30 minus 2x. Okay, and similar with our vertical side here on our drawing. So all of that is 20. All I want is what I just really bolded right there. So I want just this portion. And while it works the same way, I had 20, but I'm taking away an x and another x. So that is 20 minus 2x. Okay, so let's circle these. So these are the dimensions of the base. Okay, so this one we're going to say is the 30 minus 2x. And then this one is the 20 minus 2x. And then the x portion on our red here is the part that got folded up. So these are the pieces that got folded up. So that's x. Okay, so we want to maximize volume, and now we have our equation that can be used to maximize the volume. Okay, because volume is equal to your base times width times height. When it's a rectangular prism, base times width times height. Then we see our base is the 30 minus 2x, the width is the 20 minus 2x, and the height is x. So we have the volume is 30 minus 2x times 20 minus 2x times x. Okay, so this is the volume, and we want to maximize it, so that means we'll need the derivative, and then we will need to set it equal to 0 and then solve. Well, to find the derivative, so now this is mostly just review. If you're good at derivatives, you can jump ahead. But what we would do, I would think it's best to FOIL. So in this blue, I'm going to FOIL that out, and we will have our volume is 30 times 20 is 600. And then we'll have 30 times negative 2x is minus 60x, and then minus 40x, and then plus 4x squared. Okay, so there's the foiling, and then still this x I haven't done any multiplying with yet. Okay, and let's go ahead, let's do 2 steps in one. I'm going to write the volume here. Let's distribute this x in, but at the same time, let's go ahead and combine these. Okay, so this x is distributing in, so it would be 600x. This is minus 100x times x would be minus 100x squared, and then plus 4x squared times x is 4x cubed. Okay, so this is our volume equation, and then now I need to find the derivative, so I'm going to do v prime for our derivative, and we'll have 600 minus 200x plus 12x squared. All right, so here we've got a polynomial. Hopefully it factors. Let's see what we can do. I'm going to see, okay, so we have 600, 212. I know 2's in common with them. I'm going to take my calculator out. I want to see, I don't think 200 is divisible by 12. So I just want to check that. No, it's not. Okay, and then I don't think 200 is divisible by 6 either, but I know it is divisible by 4. Okay, so it looks like 4 would be in common for all their coefficients. But before we do that, let me go ahead and rearrange it. So I have v prime is, oops, well, I was going to rearrange it. Let me actually rearrange it. Okay, so I have v prime is the 12x. I want to see it in descending order. So let's do 12x squared minus 200x plus 600. Okay, so this is our derivative. And then now I want to set it equal to 0. So let's put that up there. 0 equals, and then I'm going to go ahead and factor the 4 that was in common out of all of them. Okay, so we're left with 3x squared minus 50x, and then taking a 4 out of the 600 is 150. Okay, so this is what I need to solve. Probably either way we need a helping hand here. All right, so the way I'm going to break this down, I'm going to go to our friend. You probably know where I'm going if you've been watching. Desmos. Okay, so let me get it open. Okay, so here's Desmos. And what I'm going to do is just graph the equation that was our derivative, the 12x squared minus 200x. Actually, let's not. Let's do one other thing in case we need radicals. So that would give us decimals. Okay, let's go ahead and use our quadratic formula. Okay, so now this 4 I could just divide over. Remember, you can divide out constants and they just go away. Okay, so that's gone. So I really have 0 equals 3x squared minus 50x plus 150. Okay, and then now I'm going to use my quadratic formula. Here's my a. So a is 3, b would be negative 50, and c would be 150. And so using our quadratic formula, we would have x is equal to the opposite of b. So let's go ahead and write it out. The opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so then let me fix that plus minus. Okay, so this is the quadratic formula, and then I want to plug all those in. So the opposite of negative 50 is 50, and then we have plus minus square root b squared. So negative 50 squared, let's go ahead and just do that. It is 2,500 because 5 times 5 is 25, and then we'd have 2 zeros attached. And then minus 4 times a, which is 3, times c, which is 150, all over 2 times 3. Okay, so that's what I want to write in my calculator. So instead of Desmos graphing, I'm going to do the scientific so that we can see it with the radical in case it's needed. Okay, so all I'm going to do is just type in what's there. So I have 50 plus or minus. So here's where I'm just going to do the plus one first. And then the square root of 2,500 minus 4 times 3 times 150. And then let me move my arrow over. And then let's divide. Oops. Let's not divide yet. Let's get parentheses. So sorry, my fault. So I should have parentheses around all of it. So let's go back and fix that. And then now let's divide. And then 2 times 3, we could just do 6 down below like that. Okay, so let's see. Let me make it better. Okay, so there's all that. So that's the decimal also. I guess if we really need to, we could have simplified and kept it a radical. I wanted to use this formula though. So that's one of our x values. Okay, so let's go ahead and press enter just so it's there. And then I'm going to copy and paste it, and let's change it to the minus to see what that gives us, and it gives us 3.923. Okay, so let's do each of these to just one decimal place. So we have two x values. x is 12.7 and x is 3.9. Okay, so let's put that right here. X is 12.7 and x is also 3.9. Okay, well, sometimes both of these might be okay, one of them might not make sense. All right, so in this problem, let's go back. If we take 12.7, so these are in inches. These are part of the box. So let's put the inches on it. Okay, so those are in inches. So if we took 12.7 inches out of the side, the vertical side here on my picture, right here, if we took that out of two parts of the box, well, that would be bigger than 20. So that's saying we're taking more out of the box than that's available. So that means this one would not work. This one is no good. This 3.9, though, is fine. You could take 3.9 out of the left. You could take 3.9 out of the right. You could take 3.9 out of the top and bottom, and it would give us the correct dimensions that are needed for the box. Okay, and since that's all they asked for, what should be the length of the side that's cut out from the square? We have it. Let's just box it up. So x is 3.9 inches. So if we take 3.9 inches, that would give us the box with the maximum volume. Okay, and if they did ask what is the maximum volume, then use this 3.9 and plug it into that guy right there. That would then tell you what the maximum volume is. This would also require a calculator, but at that point, we could find it. Okay, but I'm going to stop. That's all we needed in this problem, so we're all done. Okay, so that's it. So these are two very common rectangular problems with these optimization problems. All right, so either way, break it down. Often it requires pictures, all right? And the main thing is getting it in terms of a single variable. So like our area problem, we wanted it in a single variable on the right side. Same deal with the volume. And then once we have it, then it's just derivative, set equal to 0, solve, kind of the tedious stuff that we're probably used to by now, or I hope we are. Okay, anyway, so that's it. If you do have questions, please let me know. Otherwise, thanks for watching, and I'll see you next time.